Now let's talk about naming two-element bonds. Now this is what the whole video is going to be about. There are such a thing as three-element bonds and four-element bonds and a lot of details there, but most of the time whenever you have a three-element bond or a four-element bond, scientists have already shortened it. I think ethyl is one of the shortened things. Glucose, you may remember C6H12O6 back from a grade before. That is something that has been shortened. So it's really the two element bonds which have the rules about naming them. So first of all, let's talk about naming these ionic bonds. You may remember that ionic bonds come from metals with nonmetals. So remember, that's what an ionic bond is. So we have two rules here. You name the metal first. So whichever metal it happens to be, you name it first, and then all of them are going to end with IDE. It doesn't matter what subscript you have, but they're all going to start with the metal first and going to end with "ide." For example, NaCl, you got the metal over here, chlorine over here. It will be sodium chloride. Sodium chloride is the answer to that one. Beryllium is the metal, and fluorine is the nonmetal. So it would be beryllium fluoride. Notice they're all starting with the metal and ending with IDE. Here you also have beryllium, but you have lots of subscripts, but the subscripts do not matter whenever you have an ionic compound. It's still going to start with beryllium, and in this case it's nitrogen, so that would be nitride. Beryllium nitride. So that's how you name all of these ionic bonds. Now let's take a look at covalent. Now covalent bonds, you have numerical prefixes that tell you the number of atoms. Numerical prefixes that tell you the number of atoms. Now I know our textbook is going to have a page where you find these. And you know, many of these are just logical, but it's the covalent bonds that have the prefixes. So I'll put prefixes up here. These prefixes are numerical prefixes. So I'll just do a few of them here because your book and even the internet will have a bunch of these. Now, one is mono, although you don't use mono in all of them that have just one. But two is going to be di. Three, as you can probably guess, is going to be tri, etc., etc. So, let's see. Covalent doesn't have any metals in it. Covalent is going to be just these nonmetals. And keep in mind, you do have hydrogen, which is a nonmetal also, so that would be included in this. So, what if we have carbon and oxygen? And carbon and oxygen is CO2. So which one do you put first? You know, whenever we had these ionic bonds, you'd put the metal first. So the one you put first in a covalent bond is the one that is farthest to the left on the periodic table. Farthest to the left in the periodic table is the one that comes first. Between carbon and oxygen, carbon is the one that is farthest to the left. Now our textbook is not going to define what happens if you have like two that are in the same table. But just from experience, I noticed that whenever you have sulfur and oxygen together, you have oxygen last. So that leads me to believe that you probably have bottom to top. That's not something necessarily we'll cover much on the video. So that's the first rule on covalent bonds. You use the one that is farthest to the left. The one that's farthest to the right is said last. The one farthest to the left is said first. And then the second rule is use the prefixes. Number prefixes. So let's take a look at this CO2. Carbon, and then instead of oxide, well, they all end in IDE, but you use 2, which is di. So this would be carbon dioxide. There's a good one. What about BF3? Let's see, B and F are right here, so B would be said first. So it's boron, and what would it be here? You have 3, it'd be boron trifluoride. Boron trifluoride. Notice they end in IDE, but you have the prefixes that come before. Boron trifluoride. What about this one? N2O4. Okay, remember, subscripts mean something in covalent. They didn't mean anything whenever it was ionic. So let's see, we have the N that happens to be right here, and the O which happens to be right here. You notice I need to erase something there. Okay, so there's the O, there's the N. So you have 2 nitrogens, so that would be dinitrogen, and you have 4 oxygen, which sure enough I used one I didn't put here, but 4 is going to be tetra. So dinitrogen tetraoxide, and you usually shorten that to tetroxide. Dinitrogen tetroxide. Dinitrogen tetroxide. So do you see how you do that? You take the first one is going to be on the left. You use the number prefixes, even if it's on the left or on the right, and it ends in IDE. So you're going to have some examples of that whenever you try to do the questions. Let's talk about transition elements. Transition elements are interesting. In the transition elements, which is right out in here, it's often followed by a Roman numeral. You remember seeing in the questions we had some that had Roman numerals. In fact, why don't I go back there? Yeah, there's right here. So you know these are going to have to do with transition elements. Often followed by a Roman numeral showing the cation's charge. The Roman numeral is going to show the charge. Not necessarily the number of atoms, but it shows the charge. You know, cations and anions have a charge. All these metals over here are going to be cations because their charge is a plus. All these nonmetals over here are going to be anions because their charge are negative. So these transition elements are kind of in between, and they have a strange charge. In fact, it could be different depending on what the compound is. They don't seem to have the rules of these cations and the rules of these anions. But what you have to do is you have to figure out its charge by deducting what it is from the other element. Let's take a look. For example, we have FeO, iron oxide. Keep in mind, you'd name it just like you would an ionic because it does have a metal in it. Here's iron. We don't have a simple valence for it. We don't know what the charge is yet, but we do know what the charge is for oxygen whenever it's an anion. You have this column is all -2. So since oxygen is -2 and you have to balance them out, what must be the charge for this iron? It has to be +2. So if this is -2, which you can tell by looking on the valence electrons up here, all this in this column is -1, all this in this column is -2, all this in this column is -3, then you'll be able to figure out what it is for the ones for this transition element. So since this is -2, then you would have iron 2 oxide. And that's exactly what it is. Iron 2 oxide. So that's what you do. You have to figure out what the Roman numeral is as a result of the charge. Now, if you have something where you have like FeO3 or FeO2, then by finding out the charge of this, keep in mind you have this 2 which you have to kind of compensate for. Let's say the charge was -2 here, but you have the 2 here. So that means that would be iron 1 oxide. And yes, that happens sometimes. So keep in mind that you kind of have to make sure it all fits when you have this subscript here. Now there is one other thing I want to talk to you about. Other stuff I have put it. It is possible for several compounds to have the same formula. Here the formula for all these are, well, they're the same. The empirical formula is, remember, empirical formula is the lowest form. So we have C, H2, and O. This happens to be formaldehyde. Formaldehyde is used in the preservation of dead bodies. This has the same empirical formula, but it is different. This is acetic acid. Now, acetic acid, we don't need to use the empirical formula for. We need to use the molecular formula for it because it is just different. By adding molecules, even though it's the same proportion, it becomes a different substance. And acetic acid is C2H4O2. Now you can see that that could easily reduce down into this empirical formula, but acetic acid is just different from formaldehyde. What if we were to have this compound, C6H12O6? Hey, you remember this one. I don't know why I put a dot there. But C6H12O6, that's going to be glucose, which if you were to break it down to its empirical formula, oh, that's an awful line. But if you were to break it down to its empirical formula, it would look like this. But we don't need to break it down to that. We need to have it to where it is like this, because this is the sugar that is produced in the leaves. And this is the sugar that we end up using once we eat that. It is just different from formaldehyde, which is used to preserve dead bodies. So just want to let you know that that is that, and it also gives you a chance to see the difference between an empirical formula and a molecular formula. Hey, don't forget to go back and do these questions. Thanks a lot.